Welcome to the lesson on image intensity and color distribution analysis. In this lesson, we will see techniques for analyzing the intensity distribution of image pixel data and how this can be useful for processing images. The intensity distribution of a grayscale image is a measure of how many pixels are assigned to each grayscale intensity value. Let's go to Matlab and look at an example. Let's load in an example Matlab image. First, we read the image tire.tif. We will show it in the first of 4 subplots using the imagesc function. We can give it a title. We can label the horizontal and vertical axes. We can use the axis equal function to correct the aspect ratio, and the axis tight function to remove whitespace. In a second subplot, we will show the intensity distribution of the grayscale intensities assigned to the image pixels. To do this, we use the imhist function, which stands for image histogram. Similarly to histograms we used for data analysis, which give us a count of the number of entries in our array that take on a given numeric value, an image histogram gives us a count of the number of pixels in the image matrix that take on a specific grayscale intensity. Thus, our title is histogram of grayscale intensity values. And on the y-axis, we have our total count of pixels for each intensity shown on the x-axis. Looking at the histogram, we see there are many pixels, several hundred to more than 1,000, assigned to the very dark grayscales between 0 and 25. At grayscale intensities greater than 25, there are relatively small counts of pixels, less than 200 assigned to most, up to intensity 255. This makes sense as we look at the image. Most pixels are dark, corresponding to the tire and some of the background region of the image. A minority of pixels are light, corresponding to the ground and the rim. The result is that our image contrast in the darker regions of the image is quite poor. That is, it's difficult to tell whether the dark region is perfectly homogeneous or if it artificially appears to be homogeneous due to low light levels when the image was acquired. A basic image processing procedure we can perform to improve the contrast of such an image is called histogram equalization. With this process, we change intensity assignments of pixels in order to achieve a more uniform distribution of pixel counts across our intensity histogram. In Matlab, we can do this with the histeq function, with the image as the argument. In a third subplot, we can display the image that results after performing histogram equalization. And give it the title histogram equalized image. We similarly correct our aspect ratio using the axis equal and axis tight commands. We can also plot the histogram of the new image in a fourth subplot. Here we can see the histogram of the new image shows a much more uniform distribution of counts across the range of grayscale intensities. This is what the histogram equalization process aims to do, which is adjust image pixel intensities to achieve a uniform distribution. In the resulting image, we now can see contrast in the darker regions of the tire and rim that previously appeared to be homogeneous. Histogram equalization does not typically improve image quality appearance, quite the opposite. This image now looks rather noisy. However, it can help make visible information that was originally invisible. For example, we can now appreciate the striations around the inner diameter of the tire and have a clearer view of the outer edge of the tire.
Thus far, we have only looked at grayscale images. Now let's consider color images. An example of a color image is peppers.png. This image shows a variety of green, red, orange, and yellow peppers on a purple background. The standard approach for representing colors in our image matrix is to have not one single channel grayscale matrix, but rather 3 channels. That is, instead of just a 384 by 512 pixel matrix, we actually have 3 such 384 by 512 matrices concatenated with each other. This forms a 3-dimensional matrix where the third dimension has the size of only 3. These 3 channels correspond to the intensity of the red, green, and blue color content of the image. Each of these 3 channels can be thought of exactly the same way as the single-channel grayscale intensity image. The first channel represents the intensity of the red content in each pixel and can be assigned an intensity ranging from 0 to 255. The same for the second green channel and the third blue channel. The overall color assigned to a pixel will be a composite of these 3 colors. If we have low intensity for all 3 colors, the overall pixel color will be close to black. If we have high intensity only in red, the color will be red. If we have high intensity only in green, the color will be green. Now what happens if we have high intensity in both red and green channels, but not blue? The red and green colors mix, just as they would if we were mixing red and green paint. The red and green colors will mix to form yellow. If we have high intensity for all 3 red, green, and blue channels, they will mix to form a white color. Let's take a moment to better understand the way colors mix together. The way colors mix is determined by the color wheel. Colors of constant intensity can be distributed on a 2D plot that looks like this. To the right of center are the red colors. The further to the right we go, the more saturated the color is into red. 1/3 of a turn, or 120 degrees around the circle, is green. And another 1/3, or 120 degrees, is blue. Finally, with another 1/3 turn, we return to red. With this representation, we can think of mixing colors as the logical result of what happens when we add together these red, green, and blue color vectors, with the length of each vector from the center of the color wheel determined by the intensity of the pixel in the corresponding channel in the image. For example, a pixel with an RGB triplet of RGB1 equals 100 has a vector that points to pure red. RGB2 equals 010 has a vector that points to pure green. If we mix these 2 colors together by adding their triplets, we get a vector on the color wheel that splits the angle between the 2, resulting in the yellow color. The RGB triplet for white is 111, which falls in the middle of the color wheel. So, when we add equal parts red, green, and blue together, the colors mix to form white, which is a mixture of all colors. It should be clear from this color wheel that using mixtures of just red, green, and blue components, it is possible to create any color. Okay, back to our image. We now understand how we just need our red, green, and blue channels to form the full color image. This also means that to plot the distribution of color content of a color image, we need to plot three distributions. We can plot the distribution for the red, green, and blue channels independently. Let's go to Matlab and take a look.
In Matlab, we use the imread function to read in the peppers image. Then in our figure window, we can subplot into the first of 4 subplots our image using the imagesc function. In the next 3 subplots, we use imhist to show first the first channel, which is the red channel. This is the histogram for the red channel. The second channel will show in the third subplot. The second channel is the green channel. And finally, in the fourth subplot, the third channel, which is the blue channel. With histograms for all 3 channels, we can see how the intensity content of all 3 channels vary in our image. For example, nearly every pixel on our image contains at least some red colors. We can see this by observing there are only a small number of pixels with red channel intensity close to 0. This is because we have red peppers in our image, and the yellow and orange peppers are a mixture of red and green, so they need some red content. The white garlic bulbs need all 3 colors, including red. Even the green peppers are not fully saturated greens. So looking at our color wheel, we understand we need some red content to create duller green colors. And even the purple background is a mixture of red and blue. On the other hand, we see there is not much bright blue content in the image. Most pixels have a blue intensity less than 100, and very few pixels have intensity close to 255. Which makes sense, as we see much more red and green colors in the image.
It turns out there are other ways to represent colors defined in our color wheel. We will always need 3 channels to represent a color pixel, but those channels do not necessarily need to be red, green, and blue. Here is again our color wheel. Another common color space is the cyan, magenta, yellow color space. We can represent this color space with 3 channels that point instead of the red, green, and blue directions in the cyan, magenta, and yellow directions. With our color wheel, we see that this is simply a matter of changing our color wheel channel vector directions. While it's good to know we can change our channel colors and still represent all of our color options, this color space does not really buy us much analysis power over the RGB space unless we are specifically interested in the cyan, magenta, or yellow content of a signal for a particular application. A very different mapping of the color wheel can be obtained by the hue saturation value color space, or HSV for short. Hue and saturation are a polar coordinate representation of our color wheel. The hue represents the angle the color vector takes around the color wheel. We use red as the 0 hue reference. The angle is normalized such that the hue ranges from 0 to 1. So a hue of 0 and 1 are both red hues. A hue of 1/3 is a 120-degree rotation around the color wheel to green hues. A hue of 2/3 is 240-degree rotation representing blue hues. How saturated the color is into that hue away from white is the saturation. Saturation is measured as distance from the center of the color wheel. This is also normalized such that 0 saturation means we are at the center of the color wheel in the grayscale colors, whereas a saturation of 1 means our color lies on the circumference of the color wheel and is completely saturated into the corresponding hue. For example, this pale blue color on the color wheel is represented by a hue of 0.67, saturation of 0.5, and value of 1. The value, not shown on the color wheel, as it's a third dimension of the color space, will range from 0 to 1 and represents the overall intensity. For grayscale colors, that is colors with 0 saturation, this is equivalent to the grayscale intensity we saw in grayscale images. That is, 0 is black, 1 is white, and values between the two represent grayscales. When the saturation is not 0, for example, if we had a hue of 0 with saturation of 1, a value of 1 would give us the brightest red color. Lower values would still be pure red in color, but with dimmer brightness. For example, this color wheel we have viewed thus far is shown for all hue and saturation combinations with a value of 1. But if we change the value to 0.5, our wheel looks like this. As we can see, the color wheel looks the same but dimmer. The middle of the color wheel is gray, and the circumference has the saturated colors at lower brightness. In Matlab, we can easily convert back and forth from an RGB color space representation to an HSV one. Let's take a look.
First, we convert our Pepper's RGB image matrix to an equivalent HSV color space image matrix using Matlab's RGB to HSV function. This gives us a new matrix, HSV, which has the same size as our image, but now the three channels are the hue, saturation, and value channels rather than the red, green, and blue channels. Okay, let's see what they look like. In the first subplot, we'll show the first channel, the third channel, which is the value or the brightness channel. In the correct aspect ratio. You can give it a title that says it's the value channel. Next to it, in a second subplot, we can use imhist to display the histogram of the value channel. The value channel is what the Pepper's image would look like if we converted it from a color image to a grayscale image. It captures the overall brightness of each pixel. On the next row of our subplots, we can display the saturation channel, which is the second channel of our HSV matrix. Give it a title. And also plot its histogram next to it. using imhist. This image may look a bit unusual at first. This image tells us how saturated a pixel is into whatever hue the pixel is assigned. So, values that appear near black are very low saturation pixels, which means in the image they will appear more like grayscale colors. For example, the two very dark portions in our saturation image are the garlic bulbs, which are white, so it makes sense that they are low in saturation. Also, when the value of a pixel is very low, for example in the shadows of the image, the saturation of a color becomes noisy because it becomes meaningless. A pixel with a value of 0 shows up as black. It does not matter if it is assigned a high saturation into red, blue, or any other color. So you can notice the appearance of noisier pixels in the saturation image in the low value regions. Next, in the bottom row, we'll show the hue channel, which is the first channel in our HSV matrix. We could simply leave this as a grayscale visualization, but it makes more sense to adjust the Matlab color map to actually display the hue. This is because a normal color map is not circular. For example, in a grayscale color map, the lowest intensity from the image channel appears as black in color, and the highest intensity is white in color. But with the hue metric, the lowest hue, 0, and the highest hue, 1, are equal. They both correspond to red hues. So using a grayscale color map, these look like very different values, but they are in fact the same. So we should use a circular color map that maps the lowest and highest intensities to the same display color. We can create our own color map that permits showing 256 different hues and displays them all with bright saturated colors. To do this, we first make a 256 by 256 by 3 matrix of 256 HSV options, where the hue ranges in steps from 0 in step sizes of 1 over 255 to 1, and the saturation and value are always equal to 1s. Then we can pass this matrix of HSV options through our inverse HSV to RGB function to map them back to RGB color codes. The result is the color map we want to assign to our hue image display. Setting our custom color map to the current axes in our plot, we get a result that looks like this. As we can see, these are the hues each pixel takes on in our image. When we use the hue from each pixel and display it with full saturation and brightness, it looks almost cartoon-like. But again, this is just the hue information, not how saturated we are into the hue or the pixel brightness. Next to it, we can display our histogram for the hue channel. This can be done using the same custom color map we made by providing it as a second argument into the histogram. We also need to convert our hue image, which has values ranging from 0 to 1, into a 1 to 256 discrete number range so that the imhist function knows how to map the image intensities to bins in our color map. We do this by rounding the hue channel multiplied by 255 and adding 1 to it. Looking at our hue channel image, we can see the base color assigned to each pixel. For the most part, we see that in the hue channel, the different regions are fairly homogeneous. That is, the red peppers look like a constant, equally red region, and the purple background looks constant. In other words, these regions appear to be independent from shadow and lighting conditions. We will see later this is often a useful property for segmenting objects of interest in color images. Another thing to note is regions where things do not look homogeneous, but rather look quite noisy. For example, in the very low value, dark shadow regions. Similarly to the saturation image, when the value is close to 0, the color will be close to black and the hue becomes meaningless. But also when the saturation becomes very low, for example on the garlic bulb, our color exists near the middle of the color wheel, and the hue angle does not matter much since our color is grayscale. Thus, we see a noisy hue on the garlic bulb because we could assign any hue to these pixels and they would still appear a grayscale color due to low saturation. So, what kind of manipulations can we do to an image leveraging our HSV color space? Let's show a few examples of HSV manipulations in subplots. First, let's display our original image. Next, let's make an intensity brightened image. To do this, we make a copy of our HSV version of our image. Then we can manipulate the value channel. Specifically, if we take the square root of the value channel, this will effectively brighten the dark regions. This is because our values range from 0 to 1. So the square root function will increase our values as the square root of a fraction is a larger fraction. And the smaller the fraction, the larger the increase. So this will brighten the darker regions of the image and not have much effect on the already bright regions, as the square root of a fraction close to 1 is also close to 1. Okay, in a second subplot, we can display the result using the HSV to RGB function to convert back to an RGB color space. And title it Intensity Brightened Image. As we can see, the main effect is in lighting the darker purple background of the image. Next, how about we do something similar for saturation? By taking the square root of the saturation, we are increasing the saturation of low saturation colors in the image. We can show this in a third subplot. Again, using the HSV to RGB function to convert back to an RGB channel image. And give it the title Color Saturated Image. In this image, we can see we have not changed the image brightness, but the colors of all of the image contents appear fuller and richer. This is why adjusting saturation is a common color image processing manipulation. Hue adjustments are not as common as they tend to create unnatural changes, but we can still look at the effect. And since hue is a circular quantity, applying an exponential manipulation does not really make much sense. But adding or subtracting a fraction to the hues will have the effect of rotating our color wheel. For example, subtracting 0.1 will rotate our color wheel if we do this within the modulus operator. If we had a red hue, for example, and we added a third to the red hue, this would make it a green hue. Here we're doing a similar manipulation. We subtract 0.1 from the hue. To ensure the result again falls into the 0 to 1 range, we use the modulus operator, with the second argument being 1. This will take any value that becomes negative after subtracting 0.1 and map them back to the 1 to 0.9 range, so that the result still ranges in value from 0 to 1. We can show the result in a fourth subplot. We title it Hue Shifted Image. We can see our reds are now purples, our yellows are now reds, and our purples are now blues. This color shift makes all of our peppers look completely different. Oftentimes, the HSV color space is much more convenient for manipulating or analyzing color images. We will see examples of this in later lessons.